Okay, so hopefully you've managed to get a hold of some Elodea or some hornwort, and now we're just going to get into the mechanics of the practical and how it's going to actually work. So initially, I won't really cut any of the Elodea, I'll just take big clumps of it out of the pond. I'm looking for green, healthy, new growth. Ideally, you want to be doing this practical in spring, summer, or at least term one. That's when you're going to have your new growth. That's when you're going to have nice green shoots. It is possible to do it in the winter, but it's a lot harder. But we'll get into that later. And normally what you'll find is lots of little stems, lots of new growth coming off one big, thick old stem. So one piece could actually have 5 or 6 viable stems of Elodea that we can use. Another thing to bear in mind is that you want to be using the rosettes of the plant and not the middle sections. You want to be using the very ends of the plants. If it's a class of 30, you're going to need about 20 of those healthy looking ends. Just as a side note, I have seen it work with middle sections, but not very often. It's much more reliable if you're going to be using the florets. So now I've got my big clumps of Elodea. I'll take it to the lab, I'll give it a quick rinse a couple of times, maybe get rid of any of the debris, any dead leaves, any critters. And then I'm just going to cover it in distilled water, and then I'm just going to leave it. And before you say it, yeah, I do feel bad for some of the critters that go down there. No matter how hard you try, there's always going to be a couple, even by the time you get to the practical. So distilled water in either a bucket with some foil on top, or wrap up a big glass beaker with some foil, and that always goes on my desk so that the next day or later on I know exactly where it is, I don't forget about it. Now originally when I started this video, I was doing the foil method 24 hours before every single time. I soon realised that if I got out there early enough, I could just take the Elodea before the sun come up. I'll still cover it with foil, and every now and again I might have to get the Elodea the day before and leave it overnight, particularly if I'm doing it in the winter. So like all plants have a circadian rhythm, right? And so once the sun is in the right place, it's going to start photosynthesizing at the optimal amount. As long as we can get to it before that starts happening, we can stop that photosynthesis and then we can start it when we want. So this is what happens in high-tech aquariums when you see purling. There's an excess of CO2 from CO2 injection, there's an excess of nutrients, but there's no bubbling occurring until the lights go on. About 10 minutes after the lights go on, 20 minutes after the lights go on, you'll start seeing all the plants in that aquarium bubbling away due to them producing an excess of oxygen. It basically means the photosynthesis has peaked. People that are into planted fish tanks are always trying to get their plants to pearl. It's such a big thing in the planted aquarium hobby. And so there's loads of information out there for you to find out what nutrients are required to be in excess to be able to get pearling, which is essentially what we're doing in the practical. So that plant is super healthy, it's real nice and green. We've added CO2 with the hydrogen carbonate, and now we're adding strong light to get it to bubble. Okay, so 2% sodium hydrogen carbonate solution. For some reason, this is in percentage, weight by volume, rather than in mole, which is what we normally work in, but this time we're going to work in percentages. And I've done a bunch of different testing with this, and I've found that even 1% is fine. I've even got all the way down to 0.5%, and it's worked totally fine. So I feel like 0.5 to 2% is a bit of a ballpark. I have also made the mistake of making sodium carbonate solution instead of sodium hydrogen carbonate. You won't see any bubbling, and your plants get really soft and wilty, and that's how you know you've made the wrong solution. I've recently moved to using 1% rather than 2%. So for 1% weight by volume, that's 1 gram for every 100 ml. So if you're doing it in a litre volumetric, that'll be 10 grams for every litre. And a litre is probably more than enough. The tubes that I use only hold about 15 to 20 ml. So a litre is totally fine. And I've normally always got 1% sodium hydrogen carbonate on the stock shelf. Does keep really well, but I do tend to make it up fresh most times. I do always get the classic from the students, is this dangerous? No, it's just baking soda or sodium bicarbonate. It's probably in your cupboard at home. So the risk is pretty low. Actually, the main risk is going to be from handling the plants and the biohazards that come with pond water. So always make sure you wash your hands afterwards. And I'm sure you've noticed I'm not making this solution in a volumetric. I'm doing 1%, so I know I've got to hit the ballpark. I can be a bit over, a bit under, so I'm just doing it in a beaker. In case you're wondering, this is a travel kind of shower water pump from Amazon. Makes it really easy to be able to use distilled water on the desk really quickly. And it comes with a little rechargeable battery, so it's super easy to take it around the lab. So again, going back to the aquarium hobby, there was a real famous planted aquarium guy called Takashi Amano. The shrimp that you saw here earlier, that's named after him. He basically was the one who decided to start injecting CO2. He was doing some experiments with adding CO2 into the fish tank, and what he did was he got some carbonated water and he used that as his carbonate solution. Alright, now let's do lighting. Since I bought these Amazon lights, my life has been so much easier. They're so good. Super flexible. They're completely metal, so really robust. Nice metal clamp, so I can clamp it on the side of the desk. I don't have to worry about it falling over. So you can use it in lots of different situations. They don't get hot, so don't have to wait after handling, and just massively reduces that risk. They're nice and bright. Weirdly enough, with these you can adjust the brightness, but in the exam they're going to be looking at effective light intensity via moving the lamp away. And that'll be part of when they're studying the inverse square law, which does come up in the higher paper GCSE, about how the intensity of light changes according to distance. USB port, got a nice USB plug there. And being able to use a Chromebook is a really nice option because it gives them an opportunity to use spreadsheets and data processing, which ticks off benchmark 5 of the Gatsby Good Practical Science report, where it mentions collection and analysis of digital data. You can create a simple table, export it as a graph and print that out, and the practical and that graphing can all be done in a 1-hour lesson. And so I've changed every lamp. I've got rid of all of the old filament lamps that get hot, and I've replaced them all with these LEDs that literally just fit into one tray. And I've made this wooden block to hold 5 of the plugs. That way I can make sure they don't get lost. If you are going to use this old style filament lamp that gets hot, you have got to use some sort of heat sink, just like in the Algables practical. Just like Ingenhouse, daylight and paths of strong daylight will skew results massively. So make sure that you can black out the lab completely or as close to as possible. However, if you do see a student with one setup that's got a little path of daylight, it's really interesting to draw attention to it and question students on why we don't want that happening. We'll talk about this a bit more later, but just as a kind of caveat, of additional note, plants really like certain spectrum of light, and so these fish tank lights for planted aquariums, they've been made to emit the correct spectrum. Normally that's going to be blues and reds without any greens, and you can see that in this fish tank light. This fish tank light I've used to pre-prepare about 20 working tubes of hornwort, but I tried it in the classroom and this is not a viable way. I tried it when we had some downtime, when we were a little quiet and I had the time to prepare everything, but in the middle of a busy term, there is no way I could do this, as much as I'd like to. The other thing is it took so much away from the students. They got given a tube, all they had to do was set the light up. But off the back of that, you can definitely look at effective wavelength and how that affects photosynthesis, and you can actually reproduce that graph that's on the side of the fish tank light box. But I'll get into that when we talk about variations. The last essential bit of kit is the measuring stick. It's the ruler. This is a 1/2 meter stick, but to be honest, I was using a whole meter stick, then I was using 1/2 meter stick, and now I could probably get away with just using a ruler. I was doing 10 centimeter increments. Now I'm only doing 5. The thing that you really need to be aware of, that the students and the teachers need to be aware of, is that you have to start at 0. So the graduations at the moment, the ones I'm using, and I'm constantly reminding that the table has to start with, is 0, 5, 10, 15, 20. And that's 5 data points. That's enough for a nice looking graph. I could get away with using the students' rulers, but the half-metre sticks do make it nice and visual. And don't forget, that's going to vary from light to light, lamp to lamp. So you might want to do your own tests and experiments and trials just to get a ballpark idea of what's going to be the best increments to choose. Okay, tray's prepped, all the equipment's ready. It's now about 20-25 minutes before the experiment starts. Elodea gets unwrapped, distilled water out. We do quite a long plenary, so I might actually do this 5 minutes into the start of the lesson. But it's going to be different for every school. 1 to 2% sodium hydrogen carbonate in. It's got to be enough to cover it. This isn't going to be what the students are using, so this needs to be a little bit left over, a little bit from the stock shelf. Right, now lights on. Could use a couple of lights, one really strong light. I normally use 2 of these Amazon lamps. And normally I'll actually do this in the classroom while they're going over the method or the plenary. But sometimes I'll do this in the prep room and I'll just take it over there when it's bubbling and ready. The next thing we want to do is make a few cuts. So cut maybe 3 or 4 rosettes off at an angle under the water. Only cutting a few just as an indicator as to when we can cut a bunch for the students. So you want to be using the sharpest scissors you've got. I'm using dissection scissors. And you want to be cutting at an angle. It's been said that you're supposed to cut the stem underwater. I'm not really quite sure exactly why. Typically with floristry and with terrestrial plants, when you're making a cutting, you'd always do it underwater. That stops airlocks from happening, which is when air enters the xylem straight after it's been cut. The air will be sucked into the xylem due to the change in pressure. That blocks the xylem, stopping it from being able to uptake water. Now, obviously, that's all well and good for terrestrial plants that are sucking in water, but we're not. We're pumping oxygen out of the plant. I've cut a bunch of Elodea and hornwort in open air and it's been totally fine, so if anyone knows the answer as to why you need to cut it underwater, please let me know. So the other thing you want to do is cut it at an angle, and cutting it at an angle is going to stop blockages. It's going to widen up that surface area and it's going to give you better chance for less blockages. Remember, this arenchyma is essentially just a pipe, and what we don't want to do is use blunt instruments to cause it to close. So I think lots of teachers and technicians have recently moved from Elodea to hornwort, and they say it's so much better than Elodea. They get much faster bubbling, more bubbles. It's so quick they can't count. And so I think the reason people are saying that is because of the differences in the stem between Elodea and hornwort. So the stem itself in hornwort is a lot smaller. The air spaces are a lot smaller in the arenchyma. They're a lot narrower, whereas Elodea's got much bigger air spaces and more of them. The stem itself is a lot thicker as well. And so when you're sectioning it, you can kind of imagine what's going to be going on. So I've got hornwort on the left and Elodea on the right. Already we can see the stem is a lot thinner in hornwort, and so when you're sectioning it, you're going to be more likely to get an airlock. Okay, you're going to get a much tighter squeeze on that pipe. Whereas in Elodea, it's a lot thicker, it's a lot wider, and it's a lot stronger. You're going to keep that integrity of the pipe, which means you're going to get bigger bubbles, which means that the rate is going to be slower. And so I don't think it necessarily means that it's better at photosynthesizing than Elodea is. And don't forget, it is a lot more prone to blockages than Elodea is, but you do get a much faster bubbling. However, the bubbles are a lot smaller and a lot harder to see. Students really struggle with actually seeing those bubbles, whereas in Elodea, they're a lot more prominent. So you've put it in the sodium hydrogen carbonate, and now you've cut maybe 3 or 4 stems, and you've just waited for 10 to 20 minutes until you start seeing some nice consistent bubbling. That now means that a whole beaker of plants are ready to use for the photosynthesis experiment. And actually what you're waiting for is for the plant to get past a compensation point where the light intensity is causing photosynthesis to be equal to the rate of respiration. You want it to overtake respiration, and you want it to be photosynthesizing at its peak. Now they're going to come to me one at a time. I'm going to cut them and give them a piece of the pondweed. And then they're going to go back to their desk and run the experiment. Make sure it goes in upside down and make sure it's covered by the sodium hydrogen carbonate. They put it right up next to the light for up to 2 minutes, or until they start seeing some nice, steady, rhythmic bubbling. And that is how I describe it, steady and rhythmic, and it's got to be coming from the stem. And while that's going on, I'm going to make myself 5 or 6 backup tubes with some pieces of pondweed that are already bubbling away. That way, when a student says mine isn't working, they can come and they can get it swapped, and I can look at theirs and I can recut it again while it's in the tube. I've had it before where it's happened perfectly and I've not had to replace a single tube. And I've also had it where none of them are working, I've had to replace every single one. But most of the time, I have to replace about 4 or 5 tubes. Right, I'm just going to quickly go through some optional extras. You can definitely just use boiling tubes if you want. I got these flat bottom boiling tubes from a local lab, donated for free. They're a little annoying because they roll and they're quite brittle, but it is really easy to knock over. But in this instance, the pros outweigh the cons. Don't have to have a test tube rack or a clamp out. You might want a stirring rod or some forceps to fish out or push down your pondweed. If you keep doing it, you'll get it in the right place where it just squishes to the side. I have seen people use paper clips or something to weight it down, but you don't want to cause any harm to that erenchyma. At one point, I was using a little rubber grommet that I got from Sight Team, but it was quite fiddly for the kids to use. Stopwatches, countdown timers. Could be an online stopwatch on a Chromebook. My school doesn't allow phones, so we've got to give something. These clickers are super fun, but also can be super annoying. Very easy for them to go walkabouts. It's super annoying when you're trying to talk, so you could just be doing tallies. If you can get the conditions right, you can physically see it reacting to the light so in real time, so quickly. So here's me with my hand, and I'm literally just casting some shade over it. You can immediately see the bubbles start to slow down and almost stop, and then speed up once it's in the daylight. And it is unbelievably satisfying. That's insane.